So we are supposed to start with 2.4, the structure of atoms. Although this page holds very less information, but I'll only try to go through the ones that are important. At first, human thought that atom was an indivisible particle, which is not true. Later on, we were able to divide the atom into different kinds of other particles. It's not the smallest one. However, it's definitely considered as the most basic one. As we have previously discussed, atom is the smallest particle that can take part in a chemical reaction, so it's made up of various subatomic particles. What's important over here are the lines where they state that atom is largely empty space. Negatively charged particles, electrons are there, and they surround the positively charged center, which is known as nucleus, and the center is pretty small. The three basic fundamental subatomic particles are proton, neutrons, and electrons, and we're going to study the detail about them on the next page. Now, individual atoms are very small in size, and so far we have only one kind of microscope, which is scanning and tunneling microscopy, which allows us to see individual atoms. That we have been able to do from a decade hardly. If we go back than that, we were not able to see atom, right? Let's move on to the next page then. Subatomic particles. Now, in order to get a good idea that how small the nucleus is compared to the rest of the atom, you can consider an atom as the size of a football stadium, and the nucleus, which is definitely the center spot, would be the size of P. This is a very good example. However, to show you a complete atom, this example is good enough. And this is a helium atom. We know that helium has two protons, two electrons, and two neutrons. Take a look, the electrons are shown with crosses. They have negative electrical charge, and they hardly have any mass. They're so small. The protons have positive charge, and they have a mass of 1 unit. The neutrons have no electrical charge, and they also have a mass of 1 unit. We say protons and neutrons have almost the same mass. Now, a few things written over here are important, so I'm going to go through those. Protons and neutrons have the same mass. Electrons have virtually no mass. That is actually 1 over 1840, the mass of proton. Let me tell you, this number is a rounded off figure. You'll get to see different numbers than this if you compare electron with proton or with neutron. It's not that we're not trying to teach you something incorrect over here, but rounded off or easier figures are usually a part of IGCSE. As soon as you move on to A levels, they're going to give you exact figures and the accurate ones at that. So you are supposed to go with these figures for now. Now, important feature of all of this is that electrons and protons have charges equal but opposite. Neutrons have no charge. We call them neutral. An entire atom is electrically neutral, which means it has no overall electric charge. Now, it has positive charge because it has protons, and it has negative charge because it has electrons. So, like this, and this over here. So there you go. You have positive charge over here, and you have a negatively charged species over here. But what we do is that we sum them up in order to get our changes. Take a look. If there are two protons, the overall charge would be +2. If there are two electrons, the overall charge would be -2. And these charges will cancel each other out. We say that the charges balance or cancels each other effects. So what happens is that every atom on this planet, and mind me, I'm only talking about atoms, all right? So every atom on this planet is electrically neutral, just like written over here. What this means is that they have equal number of protons and electrons, all right? So the number of neutrons can be different, and that's going to happen in most of the cases, apart from the first 20 basic elements, in which case mostly the number of neutrons and protons would match. But for the rest of the periodic table, they mostly won't match. The number of protons and neutrons would be different. Moving up ahead, what happens is that this book caters the entire portion in a table at the bottom of this page, page number 42, table 2.7. And we're going to write a couple of things in this table. Now, subatomic particles, proton, have relative mass of 1. Remember, this is not the actual mass. This is the relative mass. How do we get these relative values? The relative values are simple. If the values are too small or too big, what we do mathematically is that if we have three different values, what we do is we divide all of them by the smallest possible value. Let's say, let me define that. If you have a number, let's say we have 2. Let me write it over here. Let's say we have 2.26, and then we have another number 3.45, and then we have another number 5.67. And if we now need to calculate the relative values, what we will do is that we need to take a ratio. In mathematics, if you need to take a ratio between random values or valued with decimal figures or scientific notation, what you do is that you seek out the smallest possible value. In this case, smallest possible value is 2.26. So you're supposed to divide all of these values by 2.26. So what I'm going to do is that I'm going to divide this one, as well as this one, as well as this one. Sorry, my bad. With 2.26. And the answers I'm going to get would be the ones that would make it easier for me. So it's 2.26 this one, and 2.26 this one, 2.26 this one. That's the way we work it out. And so now we're going to get easier random values. If you still get the values in decimal, make sure to multiply them by suitable numbers so that all the values can be converted into whole numbers. In the similar way, we have converted these mass values into 1. All right, they were almost equal, so they were 1 and 1. So happens with this one. This is not just charge, this is relative charge of proton and electron. So it's +1 and -1. So what happens is that electron's mass is very small. You need to memorize this value as well as the relative charges. Neutron, however, is 0. What you can do is you can write neutral over here. I ask my students to use the word neutral in this case over here, right? Location is easy. We already know protons and neutrons are inside the nucleus, and electron is outside the nucleus, revolving around it. This is pretty much of an easier information. Moving on. Are we clear with this one?
Yes.
Okay. I'm a little slow today because I don't have my own laptop with me. You might have to bear with me with my speed, actually. There are two important numbers that we're going to go with on this page. One is proton number. We also call it atomic number. We also call it with the symbol Z. And the second one is mass number. This is also known as atomic mass or nuclear number. And this has symbol A. These two numbers are very important. They describe atom as their characteristics. Now, everybody knows that humans are characterized usually by their facial recognition or by their fingerprints. Sometimes we even go with their iris scans, eye scans, I mean. So if there are characteristics to humans, there are also characteristics to atoms. And we have converted those characteristics into numbers for our. Can you hear me? Okay, so we were talking about the proton number and the neutron number. Now, in case of proton number, the first one, What happens is that we count number of protons in an atom. This one's pretty easy. For example, gold has 79 protons, carbon has 6, oxygen has 8. So the number of protons decide the proton number itself. It's pretty easy. We call it Z. The entire periodic table is arranged on this number. So I hope you're pretty familiar with that. Up next is nuclear number. Nuclear number, however, counts two different subatomic particles. One of them is a proton, one of them is a neutron. So it actually tries to calculate the mass. As protons and neutrons have the same mass, so they emphasize for this. Electrons had virtually no mass, so we do not include electrons in this number, actually in either of these numbers. But what's important is that you understand the proton number for any atom also tells you the number of electrons at the same time. For example, take a look at this example given over here of gold. As you can see, this one is 79 protons with a symbol small p with a positive sign showing its charge. It has also the same number of electrons, 79, with a small e as a symbol and negative as a charge, but it has 118 neutrons, so it's small n, but with a charge 0. So this 79 would be, of course, the proton number. So this depicts this one. And if we add the 79 and this 118, right? So the result would be the nuclear number or the mass number. All right? It's around, I guess, 197. So 197 would be the mass number, which gives us an idea that if we need to calculate the number of neutrons, the way we need to do it is to simply go with the formula. And teachers usually tell this formula, this is also given on the next page, is that N is equal to A minus Z. Now, sometimes the periodic table is given in such a way that the A is written on top of the symbol of the element and Z is written at the bottom. However, the other half of the word goes with an opposite method. They write Z on top and A at bottom. So the easiest way is to get an idea by looking at the key, which is already a part of your paper, that is present on the last page of the paper, one. Another easier way is that A is always going to be greater than Z. So whichever number is bigger, assume it to be A, whichever number is smaller, assume it to be Z. The only case in which this number is equal is hydrogen. And for the rest of the periodic table, A is always greater than Z, just like given over here. So the example given over here is for lithium. That's given on these last lines, and that's how it's written. So this method would be the method used in papers. So they're writing A on top and Z at bottom. I hope that clarifies it. Now let's move on. On the next page, you'll see the same formula written. So that's pretty easy. And he also explains A minus Z stuff. At the bottom of this page, you'll also see a table. Now, tables like this have been a part of past papers. As soon as you go start paper 4, most of the time from year 2011 to 2016, you'll find questions related to this stuff, to this table. But what they do as a trick is they do not talk about just elements. They may also talk about ions. So as soon as we're going to get to chapter number 3, I'm going to rediscuss this table in terms for ions. Just for a hint right now, I hope you remember that for positive ions, the number of protons is greater than the number of electrons. And for negative ions, the number of electrons is greater than the number of protons. However, for atoms, they are electrically neutral, and this specific phrase means that the number of protons would be equal to the number of electrons, as you can see in this table. Protons with a Z, electrons with also Z, as there are atoms, so both the numbers are supposed to be same. And you can simply copy this atomic number Z into both lists of protons and electrons. However, this mass number needs protons and neutrons addition. Hence, neutrons are calculated by the formula of A minus Z, which takes us to our next topic, isotopes. Now, defining isotopes, isotopes are the atoms of the same element which have same proton number, but different neutron number. So isotopes have the same proton number, but different neutron number. So I was saying that isotopes are the atom of same element, but have the same proton number, but different nucleon number. So what we can safely say is that they have the same number of protons and electrons, but they have different number of neutrons. Both the definitions can be used in exams and are also written on the next page. Okay, let's come to that page. We have a big table on this page, gives us many examples for the isotopes. We'll come to that, but a little later. Let's start with the definitions and a few important things that have been recently used in paper 2 mostly. So the atoms have the same number of protons and electrons, but they have different numbers of neutrons in their nuclei. We call them isotopes. Isotopes have the same chemical properties because they have same electron structure, which means chemical properties completely depend upon the number of electrons atoms have in their outermost shell, right? So this is an important thing and have been recently used in exams. Now, they have same chemical properties because they contain the same number of outer shell electrons. Number of electrons in an atom decide that how it's going to bond or react chemically. However, some physical properties are different. Which ones? The masses of atoms differ, and therefore all the properties that depend upon mass, for example, density, for example, rate of diffusion, as we previously discussed, they vary. So different atoms may have different density and different rate of diffusion. For example, if we start off with hydrogen, hydrogen has three isotopes as shown as in the top of this table. Let's go to the top of the table. Okay, if you take a look at it, hydrogen has three isotopes. First, by the name of hydrogen, we also call it protium. You'll find the word protium in different reference books. It has one proton and one electron, but it does not have any neutrons. The second one is deuterium. Deuterium is a little heavier. Why? Because it has one neutron and the same number of protons and electrons as the previous one. If we talk about tritium, it has even two neutrons apart from the number of protons and electrons, which is the same. Next to tritium, you'll later see a small a written. This is for a radioactive isotope. A radioactive isotope is an isotope which has number of neutrons more than what it can hold. What happens is a spontaneous decay. It automatically breaks down and it gives out energy, gives out waves, and it gives out particles such as protons, neutrons, and electrons, etc. We are going to discuss radioactivity on the next page. But before that, as you can see with every name written, what we can write, the correct way to write is to write the symbol, put a hyphen, and then write the nucleon number. For example, carbon-12, carbon-13, and carbon-14 is a good way to write the isotopes. You may also write C-12 or C-13 or C-14 in order to denote it. In a similar way, neon has three isotopes, chlorine has two, and what do you see ahead of them in terms of percentage is the natural abundance. How much do they exist in percentage naturally around the planet? And you would see that some isotopes exist in a much bigger abundance than the others. For example, neon 20, 19.5%, 21 is only 0.3%, and 22 is around 9.2%. How are we going to use these percentages? That brings us to our next topic on the next page, relative atomic masses. Now, if isotopes and atoms of the same element have different masses, then what are we supposed to write in the periodic table? Now, if you look at periodic table, you will find that the atoms, isotopes are not written separately in the periodic table. Every element is written as a whole. So how do we make it a whole? How do we come up with the value that we have written in the periodic table? You would see that the value for hydrogen H is 1, D is 2, and T is 3 for deuterium and tritium. So how come we can write just 1 under the value? You don't pick a separate isotope. What we do is that we go by a mathematical way we call relative atomic masses, which brings us to its definition. It is noted as AR, the average mass of naturally occurring isotopes of an element on a scale where carbon-12 atom has exactly a mass of 12 units. Now, in this thing, we need to understand that we compare every element with what? We compare it with carbon-12. Why carbon-12? There are a few things important with carbon-12. If we talk about C12 isotope, it has a mass of exactly 12.0000, which is pretty accurate in terms of how we measure the mass. The name of the instrument was written at the start of this topic, and that was spectrometer. However, we need not study about the spectrometer that compares the atoms, all of the atoms we have so far discovered on the planet with carbon-12 atom. Now, what we do is that when we compare it with carbon-12, we can easily find if some atom is heavier than carbon or lighter than carbon. If its mass is less than 12 units, it's lighter than carbon. If its mass is more than 12 units, it's heavier than carbon. So it's a simple way to deduce that which elements should be heavier or which elements lighter. But how are we going to come up with the mass in one single value? Because they have separate isotopes. So for that, we have a formula, and the formula is not written over here, but the application of it is written over here. Take a look at this example. They've considered the example of chlorine. Chlorine has two isotopes. The first one is Cl35 and the second one is Cl37. This one. Now they exist in a ratio of 3:1, which means Cl35 exists 75%, however Cl37 exists 25%. If the mixture were 50-50, we might have taken the mass as 36, something right in between 35 and 37. But it's not 50-50. It's 75-25. So we need to come up with a way. What's the way? To start with, what we do is that we assume that we're going to find the total mass of 100 atoms. Keeping it 100 is going to make the calculations easy. You can pick a different number, but 100 keeps the whole calculation easy. Now, if we pick 100 atoms, as per its percentage, chlorine 35 will have 75 atoms, and chlorine 37 would have 25 atoms as given over here. So what we are doing is that we are taking the mass of that specific isotope, we are multiplying it with its natural abundance, and then we are adding the same to the second isotope of it. So the second one is 35, 37, my bad, and the percentage is 25. So it's 35 into 75, then we add it up to 37 to 25, and the answer is 3550. So what we do, we started off with 100 atoms. So we divide this number by 100. That's where the part where it becomes easy kicks in. And there you go. Your answer is 35.5. So if you're supposed to repeat the same method with any other elements, it's pretty easy. Let me summarize the formula for you. Mass of first isotope, multiply it with the abundance of first isotope, add it to the mass of second, multiply it to the abundance of second isotope, add it to the mass of third or abundance of third, so on and so forth. Keep multiplying the mass and the abundance and keep adding to the values of other isotopes. Add all of them, divide them by 100, you'll get your answer. These questions have been pretty common in past papers. You would see that they have discussed hydrogen, chlorine, carbon, neon, magnesium, and sulfur mostly in past papers. So these five are pretty important. I repeat, hydrogen, chlorine, carbon, neon, magnesium, and sulfur. They're not five, they're six, right? So these six have been important, and they usually go for these ones in past papers. And some of them have even been repeated in past papers. So if you look at the top of this page, page 45, you'll find the same answer, 35.5, to the relative atomic mass of chlorine. So that's how we add all the masses according to the natural abundances of all the isotopes that we find naturally for any atom. Hence, we are capable of writing a single number in the periodic table. And no matter how many isotope an element has, and they can have as low as just one isotope, for example, fluorine or gold have just one isotope each, and they can have many. For example, tin has 16 isotopes. But let me tell you, a calculation like this complicated will not be a part of exams. They are only going to give you questions which can have a maximum of 3 isotopes. Which brings us to our next topic. Ahead is radioactivity. Radioactivity means that the unstable isotopes, and as I previously explained, some of the isotopes have neutrons that which they are themselves incapable of holding. They spontaneously break down. We call it decay or disintegration, and because of which the entire atom breaks. It breaks into sometimes smaller atoms, or maybe even just particles, such as neutrons, protons, or electrons. We call this spontaneous breakdown or decay as radioactivity. This happens through nuclear fission. I hope by now you have studied physics last block, and that is nuclear physics, and that explains two nuclear reactions. One of them is fission, and one of them is fusion. I hope you're familiar that fission is the breakdown of a bigger particle into many smaller ones, and fusion is actually the combination of smaller particles to make a bigger one. For example, you can fuse two hydrogen atoms to make an isotope of helium, that would be fusion. But if a hydrogen atom breaks down into its protons and electrons, this would be fission. Radioactivity takes place through nuclear fission. The result of this disintegration causes a release of a huge amount of energy. Uranium-235 is the common example. We actually break it down ourselves, and because of its radioactivity, we can produce a lot of heat energy, and in nuclear power stations, we produce electricity through it. So far, only 12 nations around the planet are capable of doing this on a larger scale, so much so that they can support their entire population, not 10% of their population, not entire, of course. Pakistan is one of them. Okay, decay is a completely random process. It is unaffected by temperature, and remember, it's unaffected by the fact that isotope is just a part of the compound or present as a free element. This specific statement, unaffected by temperature or a random process, has been used in paper 2 previously. Not just that, radioactive decay is not a chemical reaction. It's a nuclear process. Fission and fusion are not chemical reactions. They are nuclear processes. This also has been a part of paper 2 from year 2010 to 13. Lately, we don't see any MCQs from this specific paragraph. But we do see the uses of radioactivity in previous papers a lot. Talking about that, let's start with the radioactive dating. Radioactive dating is a way that we can find the age of organic objects. It can be the remains of humans or animals or even wood or stones. Those stones are not exactly considered organic objects, but they can still be dated. That's how we are capable of telling our children that dinosaurs were once a part of this earth. But whenever you see in or look up information about dinosaurs on the internet, you come up with specific dates that they roam around the planet this many million years ago. How come scientists are capable of telling you that they were capable of roaming around this many million years ago? This is all due to radioactive dating. Let's come to discuss it. In order to discuss it, we first need to define half-life. So every radioactive isotope decays at its own rate. What we do is that we calculate the time. The time for the radioactive sample to halve in its mass for a particular radioactive isotope is constant every time. We call it half-life. It's pretty easy. Let's take an example. Let's say we have 1 kg of oxygen 14, we can simply write it O14. It has a half-life of 71 seconds. After 71 seconds, we'll have only 0.5 kg left of it. The rest would be deteriorated with the help of this radioactivity. Another 71 seconds, and it's left to 0.25 kgs, or simply speaking, 250 grams. Another 71 seconds, 0.125 kg. So this will keep happening again and again for the specific intervals of time, and we call that specific interval of time as half-life. Simply speaking, the mass of the radioactive isotope would be halved after that specific interval. And these intervals are different for different isotopes. Oxygen-14 has a pretty short half-life, 71 seconds. Others are pretty long. For example, carbon-14 has a half-life of 5730 years. That 5,730 years are actually making us capable of finding out the organic objects and dating them even when they're millions of years old. The bigger the bodies, the easier it is for us to find out the accurate dates, because in that way, we'll be able to find more carbon-14 out of it. Remember, on the previous page, when we were studying that big isotope table, carbon-14 only existed as trace. And trace means in a very, very small amount. But for a 50 kg person, let's assume a person is 50 kgs, even that trace would be in a few grams. And that's good enough for us to measure that how old that dead body is. One important use of half-lives is in radioactive dating, and we use specifically carbon-14 for that purpose. The radioactive isotopes we were talking about, such as uranium-235 or 238 previously, and we were saying that we are capable of making electrical energy out of it whenever we use it for the peace purposes. Actually, this is one of the peace purposes we use it for. This one, if we talk about this one, it has a half-life of 710 million years, which is a pretty long one when it comes to that, right? So it can be extremely long or it can be very short. U-235 and O14 are examples for this one, respectively. Moving on. What we do in radioactivity topic, according to our course, we need to come up with their industrial usage and medical usage. There are a few industrial usage which are better explained on next page, page number 46, in terms of diagrams. Let's go through those. In a part of the diagram, you would see that they are actually using the radioactive sources to find the level of filling in containers. Industry uses very big containers, a few thousand tons probably, and will they be able to calculate the exact amount of the liquid filled in? It can't be done with a human eye observation. So what we do, we use a radioactive source for this purpose. Moving on to the B part of the diagram, we have thousands of kilometers of gas lines or even fuel lines right below the ground. And whenever there is a crack in a gas pipeline, you can't just have a car and spend thousands of liters of fuel and go through the entire country to find out the radiation leaks. It's very difficult. What we do is that we use a radioactive tracer. It's a very small amount of a radioactive substance, and wherever the crack is, it would easily come out of that. And we can detect the radiation leaks even being far away, and it's pretty easy to find where the crack lies, and then to simply repair it. The third and final use, what we see in the diagram, is the part C of diagram. And we can see we are actually converting a big piece of metal with the help of rollers into thin sheets of it. We commonly do it with iron, aluminum, and other metals such as copper. And once again, we have a radioactive source. They have written the word beta meter. Remember, beta is something that is explained in our physics book, the nuclear physics block. And beta is actually simply fast moving electrons, right? So these are fast moving electrons. If they pass through it, there's a specific thickness or thinness of this sheet. If they aren't able to do that, the thickness or thinness have increased, thickness exactly. So we can easily detect it. One use that we studied previously was producing electrical energy with the help of uranium-235. Calculating all of these, we actually have 4 industrial uses. If we talk about past papers, they usually give you 2 to write. So it's pretty easy to memorize any 2 or 3 of these. This has been a part of paper 4 mostly. I haven't seen them a part of paper 2. It has been pretty rare in past 10 years. Moving on to medical or food safety usages, that's easy. Radioactive can easily kill cells or even living organisms, the microbiological ones as well. So when the cancer cells, the cells that are growing out of control in a tissue of the body, human body, what we do is that we kill them up with the help of radiation. This is known as radiotherapy. Radiotherapy is a pretty common technique nowadays to treat cancer. And what we do is that we use specific types of isotopes for this purpose. Now, in this specific part, we have named and numbered those isotopes. So you're supposed to memorize them. Starting off with cobalt 60, it is used to treat internal cancer tumors. Tumor is a collection of dead cells or wrong cells of the body at a specific part. We usually name that part according to the body organ. If you have a tumor in your hand or in your liver or in your kidney, we'll simply call it liver tumors or kidney tumors, stuff like that. In a similar way, they talk about skin tumors. They can be treated with less penetrating radiations. Phosphorus P32 or strontium 90 SR90 can be used to treat that. Not just treating, they can also be used for diagnosis purposes. Moving up ahead, bacterial cells grow and divide rapidly. This specifically become a problem when we're talking about pathogens. Pathogens are the bacteria that can harm us in terms of diseases. They're particularly sensitive to radiation. What we do is we take our medical instruments, dressings, syringes, and we sterilize them. In past, if we go like 40 or 50 years back, we sterilized them over a hot flame. But now we sterilize them by sealing them in polythene bags and exposing them to intense doses of gamma radiation. Now, has proven to be a very effective method, and whatever instrument you see is very similar to how a microwave oven looks like. The oven that gives us gamma radiations are the same. It's just that we are in a habit of putting a yellow light in microwave ovens or a white one. However, slightly purple lights are used for these ones, the sterilizing containers, right? So this also completes our radioactivity part, which leaves us with the last topic of this chapter,